Значит, я хочу привести пример нижних оценок для динамических структур данных. Ну и сначала, естественно, определить формально, что это такое. Ну, если все-таки вспомнить, в чем идея основная, это у нас есть какой-то вход или какие-то данные, и мы хотим решать какие-то, ну, отвечать на какие-то вопросы про этот вход. Мы можем сделать препроцессинг, после чего, вот, собственно, мы хотим отвечать на много таких разных запросов. И, ну, причем хотелось бы отвечать на них очень эффективно. Там за алгоритм времени или там за константу даже времени. Но если это все, что требовать от структур данных, то это называется статические структуры данных. А динамические, они должны еще поддерживать апдейты, то есть которые могут как-то каким-то образом модифицировать вход. А потом про вот этот модифицированный вход какие-то новые вопросы задавать. Вот. Ну, и, соответственно, это все будет на примере задачи о вычислении многочленов. Сейчас, значит, сначала я определю задачу, ну, в общем виде, что такое задача для динамических структур данных. А потом на примере покажу это определение на примере задачи вычисления многочленов. Polynomial evaluation. Значит, ну, тут надо задать кучу конечных множеств. Конечное множество d – это, ну, как бы множество входов. Значит, конечное множество q – это множество возможных запросов. То есть я сейчас определяю не что такое динамическая структура данных, а какие задачи они решают. А потом я определю, что такое решение для задачи. Как бы множество запросов. Потом множество апдейтов.
Сейчас, это есть в общем случае?
Да, в общем случае.
Зачем нам разговор про многочленов?
Ну, как мне определить, что значит... Okay. So you don't want a general definition?
No. I don't want any general definition.
Okay, let's try to do it without a general definition. So in polynomial evaluation, but I should at least define data structures for polynomial evaluation, what it is in general case. Okay, so in polynomial evaluation, what we have a set of polynomials if coefficients in some finite field, let's say a prime field, of degree at most n, less than n. So to specify such a polynomial, we have to specify n coefficients, for example. And what we want to do, we want to answer queries of the form. What is the value of h on some element of a field? So each query is specified by an element of a field. And we want to maintain some kind of updates to polynomials. There are several variants. The most simple for proving lower bound is just to allow to modify a coefficient. Let's say, so each update can be specified by an integer from 0 to n minus 1 and by an element of a field. And this update, such an update, acts on a polynomial like a set. It's just a set the coefficient before x to the I to rho. So it will be the same except for the I coefficients. Okay, so once again, what the task we want to solve? What kind of task we want to solve?
So every update is specified by two numbers. One
Yeah.
is a row, and the second is one is y, right?
Yeah. So once again, what we want to do? We want a data structure which does the following. It can, in any time, in any point of time, it can answer a query of the form, what is the value of our current polynomial on a given point of a field, and it can maintain updates of the form change the coefficient before x to the I to something. And maybe if we will have time, we can consider another kind of updates. For example, we can assume that our polynomial is given as a product of linear terms. It is as a product of less than n linear terms. And once again, the queries are the same. And for example, for updates, you can remove or add some linear term to your current product. Okay. So
this was an example of a data structure, right?
no, it was an example of a problem for data structure.
Say it again. What is the problem?
The problem is to have a data structure, something I didn't define yet, which is able to answer queries of the form what is the value of a polynomial on a given point, and which can and which is able to maintain updates. Let's try to first consider this type of updates in which use just a set coefficient of a polynomial, some coefficient to something.
And that line.
And this is another variant. Maybe we will consider it
Type of updates.
another type of updates. Okay, so let's define what is a solution. What is a dynamic? Let's say define what is a SW T update T query dynamic data structure for this problem. So here SW T update and T query are some integers. So to specify this thing, we should specify, first of all, so informally we will have memory. Our memory will be a string of length s over an alphabet of size 2 to the w. So we will have w cells, or we will have s cells, each of w bits. So first of all, you should specify an initial content of your memory, for example. So it will be a string capital S0, which will be just a string from here. Okay. Then for every query we should specify how we deal with this query. So for every possible update, which is an element of a field, we have a decision, let's say read-only, in brackets, read-only decision tree T gamma over 0, 1 to the W to the S. So what it means? That decision tree, so it means that it, for example, in the beginning we can read a decision tree, such a decision tree can read the content of some cell. Let's say the ith cell. And then depending on what is the value of the ith cell, so it at the unit cost, a decision tree reads all W bits in one cell. So and then there are 2 to the W possibilities, depending on what is the value of the ith cell. So the arity of a tree will be 2 to the W. Okay, and then it can read some other cells depending on the previous reads, and so on. So in the end, in the leaf should contain the answer to the query, so the element of a field. Let's say H gamma. No. Some. I don't know.
So
X.
you are explaining now how queries are answered using in a data structure, right?
Yeah. And the depth of a tree should be at most T query. So this T query is just a time, corresponds to a time which one query takes. And we only count a number, so we only count how many times we read a cell of memory, and we do not count any other practical issues. So
so you do not care how you update your...
Yeah, so for example, I don't care if I read the ith cell, and then I should decide what to do next, and how many time it takes for me. It takes, so something is wrong there. Here.
No, the question was whether you have explained up to now only how you answer the query, right?
Yeah.
But there is also there are also updating operations, right?
Yeah, right.
So you do not care how complex they are, updating operations.
Yeah, I don't, but I didn't define what.
So okay. You will proceed.
Yeah, just was explaining this.
Доклад не кончился, в смысле, да?
Okay. So, and for every update, which once again is pair of a number and an element of a tree, we should have also a decision tree, but now this decision tree can also write something in a memory. So it will be, let's call it read-write decision tree T I row, once again over 0, 1 to the W to the S, now of depth at most T update. So what it means that read write. Now we can query cells as before. And it can also write something in some other cells, and in some cells. So, for example, first it reads the ith cell, and depending on what is written in the ith cell, you can query the cell number j. You can read the cell number j and write something in the kth cell, and so on. Then you can query some other cells, write something in some, and so on and so forth. But the depth of the tree should be at most t update. Okay?
So for updating, you have some parameter t, and for read one and for
T update.
queries,
T query.
t also the same parameter. So
No, T query. T query and T update are possibly two different numbers.
Sorry, you have two parameters. T
Yeah.
update, t query, yes, and W. Okay.
Okay. So I don't know. We can. So when we should say when this works. When for every sequence of updates in queries, whenever we have a query, it is answered correctly.
Mm-hmm. So, for example, if you just want to copy from us one cell to another one, it's one query.
If you want to copy
Copy. No, I mean you want in your data structure to copy one cell to another one.
the queries, you.
No.
I think
query.
so.
I mean.
No.
updating
It's something
operation.
is not clear. Queries are elements of a field. The result of the query.
Sorry. In your decision tree,
Yeah.
when you evaluate one cell,
Yeah.
how you call it? When you are. So you have a cell,
Yeah.
another cell. You
Yeah.
want just copy this cell to that other cell.
Yeah.
So you can, for this, you can build a decision tree of
Depth
height.
2. Depth 1.
Depth 1. So
I think so. You can read the some cell, yeah, and depending on the result, you can write in some other cell its content, which
So
is
that's-
specified by this h.
So depth 1. Okay.
Yeah, depth 1. Okay, so I don't know. If this is all clear, and it is clear what means that the data structure defined as follows solves correctly this problem, which I defined, then I can state a theory about lower bounding this. Okay, the theorem is as follows. So we will have a kind of a trade-off between update time and query time. So we will say that it is not possible to for a query time and update time to simultaneously be small. And what we can say that this is a theorem by Larsen, which says the following: if we have S W T update T query dynamic data structure for polynomial evaluation, as given here. And if the size of a field is n to some constant which is larger than 1. So here are conditions of theory. And if s is at most 2 to the w. So this is what it means really, that you can store in one cell a pointer to some other cell at least. Okay? And if w is O of log n, when once again n is the degree of a polynomial, the bound of the degree of polynomials, and if the update time is polylogarithmic in n, this implies that query time should be large, at least something like log, let's say, to 1.9 log n to the 1.9.
So what is n here?
N is the bound on degree of polynomials. Look here. So I will use this definition. So I have polynomials of degree at most n and p element and a field of p elements. And I want to solve this task. And p here is the size of the field, n is the degree. Okay, so so I wrote here 1.9, but you can actually obtain any constant smaller than 2, but to be specific, let's consider 1.9. Okay?
Any constant less than 2?
Yeah. It will be strange if any constant bigger than 2.
Why? So, okay.
Okay, so what is...
But maybe to understand this theorem, maybe we consider some simple examples of, an example of the trivial data structure. What
trivial data structure for polynomial population.
Just keep all the coefficients, right?
So, yeah, so tell me the trivial.
So we keep all the coefficients, right?
Yeah. So S.
So W, S is n, W is log p.
S is n, W
is log p.
Is log p.
Now we need T update is 1, right?
Yeah.
Just to need update one coefficient. A T query will be.
The query you should. Yeah. The query should.
So we need anyway to know all the coefficients. Okay. So.
So this doesn't contradict the theory.
So wait, n is at most 2 to the p. That means n at most p. If I just want to see if the conditions are satisfied.
Yeah.
So we can assume that n is less than p, right?
Yeah. So okay, and once again, let's assume that
But
P is O of n. So here I require that P is larger than n significantly. But now let's solve our problem when P is just a little bit bigger than n. I guess we can we can just, what we can do? We can just store all the values of polynomial. Yeah. But we should. Yeah, but this will be a problem if you store all the values of a polynomial. Yeah, and you have an update which sets some of your coefficients to something. You should modify all the
everything. So t update will be n?
Yeah, t update will be n, and t query will be constant. And you actually don't need, if you care, you need this assumption. You don't need this assumption. You can store all the values of a polynomial using log p bits in each cell and using p cells. And then if you have a query, you just need to read one cell. And if you have an update, you should update all the values. So the update time will be actually not n but p. So we have two extreme databases, and in each one, in the first one, we have a constant update time, but a huge query time, and the other way around here. Okay.
And Sasha is also asking, Sasha Shane, what happens if we do not need updates, just answer queries?
Okay, so in this case, we can prove that a query takes log n time.
But is it possible to achieve log n?
I don't know. We can. The lower bound. This is a static. When we do not need updates, this is what is called static data structure. In this thing, you can prove a lower bound, which says that if you have a memory which is linear in n, then you should. And the size of the field is also a little bit bigger than n, then the query will take log n time, at least. On the other hand, from the upper bound point of view, in a static regime, we know that it is possible to evaluate polynomials using just a little bit more than linear space. So you can have this S like that, where delta is any constant. And a query time which is polylogarithmic. And here the constant here depends on delta. So this is what we know in static regime. And
so if we allow a little bit more space, then we can achieve polylog. But if we require, if S is n, then we do not know any upper bound better than n. This is exactly reality.
Yeah, I don't know.
Or order.
I don't know. Yeah.
Okay.
But for that, but this upper bound doesn't. I don't know whether something is known for dynamic regime, because it is harder to design a dynamic data structure. And I don't know whether something non-trivial can be done. But okay, so in a static, for static we have log n lower bound, and here we have something which is almost log square.
So again, Sasha is asking for the lower bound. log n.
Yeah.
In the static regime.
Yeah.
There is, what is the assumption about p? So, we do not, how p and s are related.
Okay, static, let me write a static lower bound result. In static lower bound, we don't have update time, but if S is linear in n, and if W is all of log n, and if P is n to the power of something strictly larger than 1, because, okay, then I guess that's all that you need. Then query time should be logarithmic.
But wait, what is the total memory we have now? P to the W is polynomial in n times s. So in theory,
no.
I mean, you have enough space.
You mean a bit? How many bits you have in the memory?
Enough to store all the values.
No. What you are asking? You are asking how many bits you have in the memory? Yeah.
Yeah, the total capacity.
So, and what is your? And what you think it is?
In this case,
yeah,
it's enough. I see.
No, enough. What is it? You say it's 2 to the W multiplied by S?
Yes.
No, it's W multiplied by S.
Ah, sorry. It's W multiplied by S.
Yeah.
But that means.
That means that, okay, you can store n cells, each of log n bits. So the bit length.
We can't store all the values of the polynomial.
We can't store all the value because if you can store all the values, then you don't have to do updates. Then the query will be constant. But to prevent from this lower bound requires that the size of the field is significantly larger than the degree of a polynomial. Okay? So let's proceed to a proof.
Of Larsen.
Yeah. So these both results are due to Larsen. And the static lower bound and the dynamic lower bound. In 2012 or something like that. Okay. So let's take n alpha 0 alpha n minus 1 and gamma independently uniformly at random from a field. And we will only require that our data structure works correctly in the following scenario. When at first we receive n updates and then we make one query. So let me write it. We only need from data structure that it operates correctly when we first have n updates. The first update sets the coefficient, the coefficients between x to the 0 to alpha 0. Then we have an update which sets the coefficient before x to alpha 1, and so on. So this will be updates, and then we have a query, gamma. Okay? So it looks a little bit strange because we are proving a dynamic lower bound, but we do some updates. So in the end, what will be a polynomial in the end here?
It's written when doing alpha 0 plus
Yeah.
alpha 1 times x and so on.
Yeah. But what is crucial here is that, so it looks like we receive these coefficients, we preprocess them somehow, and then answer a query. But the point here is that the time you have a limited, you have only t update time to process each coefficient. So you cannot process them simultaneously, do something global with them. You receive a coefficient and you do something in t update time. And that's always the first coefficient. And you don't remember it after that. And later I will explain also why we need to choose them at random. This is because of linearity of expectation. Okay, so what I will do next? I will now, let me draw a timeline, a kind of a timeline. And I will draw all updates on this timeline. The last will be, and then I will define several random variables. So these are random variables. And I will define several random variables which will be tuples of this. Okay? And I will call these random variables epochs. And I will enumerate them maybe a little bit strangely in reverse order. So the first epoch is just the last coefficient, and I will denote it by E0. Then then I will have epoch E1, which will contain now, which will be a tuple of beta coefficients, starting from alpha n minus 2 and beta minus 1 more coefficients. So beta is some parameter which I will choose to be like t update omega multiplied by omega squared. It not much, doesn't matter much, but okay.
Okay, now it's not evident why you use
It's
this
not
formula,
evident.
but
It should not be evident. I can.
Okay.
I just want
So
to.
we will choose some parameter
Yeah.
and consider B coefficients preceding the last one.
Yeah.
And
And so on. I will proceed as follows, and I will define an epoch I. It's. I will say that here I take beta to the I coefficients. Okay. So, like you can imagine that so first I take b to the 0 coefficient, so just one coefficient, then beta coefficients, then beta squared coefficient, and so on. And these are random variables, some random variables. You can imagine that why I don't know why they enumerate like that. Just because we need so that the size of the epoch grows from here to here. Okay, so the larger epoch is, the more far it from here. So you can imagine that this is a BC, before Christ. So, and this enumeration like okay. So now what I will define? Let me define. So, okay, I will not erase a theorem sometime. Let me define. So, when we are dealing with these updates, something happens to our memory. So we have S cells of memory, each containing W bits, and let me define Ci as the set of all cells which were used in epoch I but not in all the remaining epochs, but not in EI-1 and E0. Okay. So is this definition?
So they were used for the first time, so to say.
No, the last time they were used is
the last time.
The last time they were used.
But when you call SL used, you mean that it was either read or?
It was either read or something was written in it.
Or written.
Okay.
Okay.
So for example, you can upper bound this S4. So how can you upper bound this? This.
At most is the bit to the E, I guess.
Yeah, but you should also multiply it by T update, because each new update uses at most T update cells, and we have in epoch I we have at most B to the I updates. Okay? Or
but why do you multiply by T update?
so we have that many updates in epoch I. Yeah? And how many
and what is CI? Set of cells
which were used last time in epoch I.
So it must beat to the I. We don't need multiply by T update.
Okay, so beta to the I is the number of updates. Yeah? In epoch I.
No.
So
beta to the I is just the size of E sub I, right?
yeah, and what is the size of E sub? So E sub I is a tuple consisting of alphas.
Yes.
And so it's a tuple consisting of coefficients. So in each EI we have B to the I updates.
So we need to multiply.
Yeah.
And Sasha also is asking whether in the definition of C sub I, we care whether they used before epoch.
No, we don't care about.
We do not care. Okay.
They may be. They could be used before that. So the second observation is that all these CIs are disjoint. Just by definition. Because for each cell we can consider the last time this cell was used. So all these CI are disjoint. Okay? And also know that CI is a random variable once again. It depends on alpha, on the values of alpha. So since alphas are random variables, then Ci is also random variable. Okay? Now, this will be a crucial thing. Now, let me define. So we can ask ourselves. So we have a random query gamma. How many bits? So this query reads some cells of memory. At most T query cells. So we may ask ourselves how many cells gamma reads in Ci. And let me denote it by Ti. Ti is the number of cells a query gamma, which is also, once again, these are all random variables. And in a minute, I will explain why we need this. A query gamma reads in Ci. Okay? Now, what is important? It is important that for any possible, so with probability 1, T query is it.
By the way, I forgot, for every gamma we have a special decision tree, right?
For every query.
Yeah, gamma you call
Yeah,
gamma.
for every gamma. And we just look how many cells this
For
decision
that
tree.
particular decision tree reads in Ci.
Yeah. And the claim is simple that T query is at least the sum of all Ti. For every outcome of random variables Ti. Because Ti is the number of cells, which we read in Ci, and all Ci are disjoint. So whenever alpha 0, alpha n minus 1 are, whatever they are, we know that we can, the values of Ti, their sum is at most T query.
So the only thing we need for this bound is to pairwise the jointness of Ci's, right?
Yeah.
Okay.
Okay, then it also holds that expectation of their sum is at most T query. And then, due to linearity of expectation, we have this is the same as the sum of expectations. Ti. Okay? This is why we need distribution. So, okay. And the main claim, the core of the proof is to prove that all these Ti are big.
Or expectations are big.
Or their expectations are big. The main claim is that for all, let's say.
So wait.
Yeah.
Sasha, wait. And now that Sasha is asking, can you just explain, maybe very vaguely, the main idea in only one sentence?
Okay, the main idea is to prove that all these expectations are can I use what I have already explained?
You can.
You can. The main idea is to prove that this expectation is large for every I. We will prove it by contradiction, assuming that for some I, this expectation is small. Then we will use compression argument to obtain a contradiction. Okay? So for so the claim is that for every I which is bigger than some constant, it holds that expectation of Ti is at least log 0.95 n. Okay? So what if we assume that we have proved this? Then what do we obtain? We obtain that T query So, how many epochs we have?
It's not easy to calculate. So more or less, we need to find the largest I such that b to the I is less than t update. Oh, less than
We have n coefficients. We define them into several groups.
N. So beta is beta.
So we have log n based beta.
Oh, yes, exactly.
We have that many, except for a constant number.
Okay. Log.
And each expectation is log 0.95n.
What is beta? Have you erased already?
I have erased this. And beta, once again, is t update w squared. So what we will have here? We have log n multiplied by this log divided, so it will be log 0.95n divided by log beta. And beta, recall, this is this thing. This is log n omega.
So
So
this will be log n, very small.
Yeah, this will be some polylog. This will be log log.
What is t update? Also log n.
It's polylog.
Everything here is polylog. So in the denominator we have
Polylog.
Log n.
Oh, log log n.
Log
Yeah.
log n. Okay.
So if we prove this claim, then we are done. So from now, to do so, we will use contradiction.
So what will you describe using a very small code?
I will describe EI.
EI, the set, or what?
Well, it's a tuple.
EI is the set of coefficients. So
It's not a set, it's a sequence.
sequence. So you will describe EI for that I for which this is not true, right?
Yeah. So I assume that for some I, this is not true. I will consider the following compression task. So there will be, so for some I, this is not true. The claim is false, assuming that. Okay, so this is an assumption. Claim is false. We will have a receiver, sender, and the receiver. The goal of a receiver is to output EI. But okay, let's be. So what sender is given the whole sequence of coefficients. Alpha 0, alpha n minus 1. Okay? And receiver is given all the epochs okay, let's say all the epochs before the epoch number I. It's some additional information for him. Then sender sends some message, which is a binary string, which is a function of alpha. And then a receiver should output using a message and this additional information which he knows, he should output EI. We allow him to error sometimes. Let's say he should output EI with probability 0.99. Okay? And so you can prove.
So Sasha is asking sender and receiver how they are connected to you were talking before. I understand that sender and receiver is a way to explain these coding, these compression arguments. So the sender will compress.
Yeah, the sender will compress, but
Actually, we could state it without sender and receiver, but Sasha,
yeah, okay, but it should be stressed that receiver or something who decodes the message of sender knows this thing.
So anyway, we want to compress EI conditional to all the epochs preceding EI.
Yeah.
And that's it.
Yeah.
Okay.
With some error probability.
And we allow small error probability.
Probability over alphas.
What is M sub alpha? M sub alpha is just the compressed code of EI conditional to all the preceding epochs.
It's a function of alpha.
Okay, it's a function of alpha, of course.
Yeah. It's a binary string of some length. Okay. And you can show, I don't know, that it's kind of the standard fact of information theory that in this regime you need, let's say, the length of our message should be at least it should be at least 0.98 beta to the I log p. So what is this thing? This is a number of bits you need to specify EI. Okay? So this is log of the number of possible values of EI. So if there is no error, then you should use that many bits.
Mm-hmm.
But you have some error, and from something like Fanos inequality.
So we pay for error. I mean, we pay by increasing the coefficient to 0.98.
Increasing?
I mean decreasing. Sorry.
Decreasing.
So it's
our lower bound becomes weaker because we have error. Okay?
So it's Fanon inequality.
Yeah. So okay, if time remains, I can explain this, but it at least looks
Intuitively clear.
yeah, because receiver has some information about, but okay, so all these things are independent of EI. So this information really doesn't help much in encoding EI. Okay, so now let me state the main lemma of the proof. And then, okay, I'll try to explain how to. So when we will obtain, assuming this, we will obtain a contradiction with that. Okay, so the main lemma states the following. Let's say with probability 0.99 over alphas, there exists a set of cells R, which is subset of Ci, such that First of all, the size of R is small. It should be small o of b to the I log p over w. And it should be the case that at least n queries do not read. I don't know. Is it possible to see something here? Do not read cells from Ci minus R. So we can take a concise, just a tiny set of cells such that many queries read only these cells if we are talking about Ci, and the size of R is small. Okay?
When you say at least n queries, you mean there are at least n different gammas, right?
Yeah, there are n different gammas. Okay, so how, using this lemma, we can obtain a contradiction with this? So now I will explain how to use this lemma to devise a coding scheme. So first of all, we send we send all the epochs after the ith epoch. So, then we send R and its content. So recall that R is some set of cells. So we should specify where are these cells and what is written in these cells. So namely, what is written in them after the ith epoch. And we should also send a location and the content after the ith epoch of all cells used in EI and later. So recall the definition of Ci. It's the these are all cells which were.
So right, I think this is the location and the contents, right?
Maybe Z.
Yeah, sure.
Like this whole, right?
So the location and the contents of all cells used in II and later.
So we have Ci.
So, but they might be changed several times after it.
Yeah, might be changed.
And so for each change we need to send.
No, we send their content after EI.
Immediately after EI.
Immediately after EI. Because it's enough for us because we will also know all this. So recall Ci are all cells which were used in EI and last time. The last time they were used is EI. And
later they won't be used.
Yeah. And this is a little bit different. We require that they used in EI and at least one time later. Okay, so how then to restore EI from this information? So receiver now knows all this, and he takes the initial state of a memory in our database. And then he starts to simulate updates. So first of all, he knows all the epochs before ith epoch. He does he
performs all the updates.
He performs all the updates from this app. Yeah.
Up to the epoch I.
Yeah. Then, okay, so then he doesn't know EI. But these updates do something with the cells. Okay, we don't know them, but we know a part. We don't know what happens with the cells after EI, but we know what happens with a part of the cells.
Which part?
R. Okay, because we send them. We know what will be the content of R after EI.
So, say again, what is R? R is R is a set of cells.
Yeah. And also some other cells which were used in EI. Some of these cells we will need later. Okay? And we also know their location and their content. Because we also obtain this information.
Wait. Including the cells that are used in the updates during EI?
Yeah, which were used in EI and later.
But then the whole number can be larger than the size of EI, right?
No.
Why? With each update is allowed can touch a different cell, for example. Then
they were used later, so you can
use both in the EI.
You can upper bound them by the sizes of all the later epochs. Okay? Okay. Then he proceeds with the simulation. So he also receives the remaining epochs. And he looks, so he performs these updates, and he does
so maybe I understood the plan. So Sasha keeps asking, what is the plan? So your plan, I now guess, is the following. So we know those, we can assume that we know those n queries. So those specific n gammas.
Yeah.
So we simulate everything and then ask all those squares,
Yeah.
one after another. So we obtain the value of the polynomials. So
Yeah.
we know now n values, and so we can recover the total polynomial from n values.
Yeah.
And after that, we can actually, we know all the coefficients. Because when we know n values of polynomials, we know all the coefficients. In
Yeah.
particular, we know all the coefficients from EI.
Yeah.
So that's the plan.
Yeah. So and this is enough information to do this plan. Because if there are at least n cells which do not, so the only problem in our simulation will be cells from CI. Yeah. We don't know what is written in there in the end. We only know what is written in a part of this cell, in R. But there are at least n cells which do not read the remaining cells from CI. Hence, we can simulate the queries for these n elements of a field. And then we can recover the polynomial. Okay?
So, Misha, have you gone through? Yes. So, Sasha asking if somebody understands what's happening, let him explain. So, that's you who understand. So, now you well,
Just the overview.
I mean, now we can try the second feature. So, Misha takes the microphone and tries to explain.
Well, as we know by now, this microphone actually records everything regardless of...
No. The questions are very badly written, actually. I mean, Simone's question was not understandable, for example. And mine was because I am closer to this now.
Well, I think that, well, the general overview of this proof is as follows. That we have the later epochs, and the total size of the later epochs is smaller than than the size of the current epoch, and it is, well, by tuning better, it will be smaller than the gap we need to close anyway. Then we have all the locations and the contents that will be used after the current epoch. As far as I understand, saying that they are used in EI and later, I'm not sure it does change anything if we just say that they are used later.
Okay.
Right? Yeah, and so again, their total size is limited by how we have the later epochs smaller than the current epoch. They are all smaller, and now we need the beta to be smaller than T update, right?
Okay.
Yeah, and so what we want to say that the first part and the last part are just significantly, if we tune the beta, they can be made significantly smaller than the size of the current epoch. And R, by assumption, has to be significantly smaller than is allowed by Fanon's bound.
Yeah.
Right?
Yeah.
I think that, well, the overview, the idea of the proof is that, and then you need to go to details, and I cannot do it as well as Sasha. Yeah. So it's back there.
Okay. So once again, a plan. We have to obtain a contradiction with that, assuming that expectation of Ti was small. Then, okay, we first of all we haven't proved yet this lemma, but assuming that this is proved, we try to obtain a contradiction with that. We design a compression scheme, and
yes. So did you write the numbers to
Yeah.
see that we obtain a contradiction?
Yeah.
Okay.
So let's write that. To send this, so how many coefficients are there?
More or less beta to the e minus 1 times.
Yeah, so it's beta to the minus I times log p. This is small compared to this. This is all of this, or little all of this. Then to send R in its content.
But wait, you have already raised what is P.
P is the size of the field.
Ah, I see. It doesn't matter what is beta, because to see this we just need beta is growing.
Yeah.
Okay, good.
Well, we need that it grows, that beta is not constant. So this is a little. Okay, then we also need to specify R and its content. We need the size of R multiplied by W. So we need to say where are cells from R, the location of R, of all sets in R. To specify location of a cell, we need W bits because S is at most 2 to the W. Okay? And
Why we multiply by W?
okay, we have to specify.
Because this is the number of cells in R,
Yeah,
and
yeah.
each cell is W.
Yeah,
It has length W.
yeah, and we should also specify its location and its content. But we have assumed that the size S, the number of cells, is at most 2 to the W.
Yes.
So to specify location of a cell, we also, it is enough to have W bits. Okay, so this takes this many. And this is also little o of this.
But wait, you have specified in W bits the locations, right?
Yeah.
But the contents.
And also W bits.
Ah.
2W, but this is little o, so
I
it
see.
hides everything. Okay, and to specify this, so how many cells will be used after epoch I? So if it's used later, then we should take a number of updates after the I epoch. This is something O of b to the I minus 1. Okay? And each update uses at most T update cells. And now recall what is.
So this should be plus, Sasha. So I mean.
What, here?
No. You have written 3 terms. Okay.
Yeah. Okay. So now we have to recall what is beta. We should. So let's write it. We have this, and let's write it that this is bi to the I log p. So I just rewriting this. Okay, and we should also multiply it by w once again, because this is the number of cells which we use, and to specify them, their location and content, you need O of w bits. So this is.
So we want to compare it with b bit to the e log p, and that's for you are writing.
Yeah. So this is b to the I log p
over
beta, and here I have w t update.
And also log p in the denominator. Because you have multiplied by.
Yeah, I also have a log p. But, okay, but recall that beta is squared this. So this is also little o of this. Okay.
But up to now, it's not clear why you consider beta square of that and not just that.
And what you want to be beta?
No, just W times T update, for example.
Okay, it also works.
Okay.
I guess. Yeah. So now, let's try to understand the lemma. Okay. How we will prove this? First of all, the first step. So recall that we assume that that the expectation of I is small. Of t, I mean, the expectation of ti is less than log 0.95 of n. Yeah? First of all, we will use this to show that with probability, let's say, once again, 0.99 over a choice over alpha.
So you're proving the lemma?
Yeah. With probability 0.99 over alpha, at least so almost all queries, so recall that queries are elements of a field, and I say that almost all queries, 0.9 queries, be it at most, let's say 10 to the 5 cells in CI. Okay, so should I recall what is TI?
What is what?
TI, T sub I.
T? There is no T sub I here.
Here it is.
T sub I is the number of cells from CWI. Oh, sorry. No, you need to do this.
T sub I is a function of alpha and gamma, and this equals the number of cells gamma reads
In CI.
in CI when the updates are as alpha. When updates are alpha. Okay? And we assume that expectation of this thing over alpha and gamma, for random alphas and gamma, is small. Then we are claiming that, again, intuitively it is clear that if expectation of this thing is small, then almost all queries ask maybe a little bit larger than this.
But what is written here? At least 0.9 p.
Queries here.
And this is p. What
Yeah,
is
P is the size of a field.
Sorry.
P is the prime number.
So p is the prime number.
Yeah. Queries. So we assume that on average, the query reads a small number of bits in CI.
Okay.
Then
that means that many queries
with small number. Just a little number of.
So it's very plausible, at least.
Yeah.
Very easy to believe.
Again, this is not not very interesting part. It's like two Markov inequalities. Okay, so now let's deduce from this. Okay, this is technical part. This is not. This is what is called self-sampling. So, okay. So how I will choose R? I will choose it at random, and I will use a probabilistic method to show this lemma. So I will sample. So I will take R. So I have all the cells from Ci, and I will choose, and for each cell I will draw a coin.
So here it's not important how Ci was defined at all. So we can see we have just a set.
Yeah. We have just a set, and we want, and we know that for many queries, at most that many cells are read on. Okay. So we take each cell of Ci with probability theta, which will be some 1 over polylog of n. I don't know how. Okay, it will be specified later. With this probability, we take each cell. Okay? And let me define that a query is awesome for alpha if it satisfies this restriction. I mean, a query is awesome for alpha if this query does not read cells from this. And the goal of lemma is to show that, so R was chosen at random, and we have to show that with positive probability, the number of awesome queries is at least n, and then we are done.
Awesome, you use awesome here in a positive sense.
Yeah. Okay, so let's take an expectation of a number of awesome queries. Let's write something like that. I claim that now alpha is fixed. Yeah? So we fix some alpha for which at least 0.9 p queries are as written here. Okay, so now I claim that so I want to lower bound an expectation of a number of awesome queries. I claim that multiplied by p. So and no. So here on the right, I have an expectation of number of awesome queries. And I claim that this is at least this. Why is that? Because I have 0.90 or 0.9p queries which read at most that many cells in CI. What is the probability that all the cells which such a query reads are in R? Recall that how R is defined. We include each cell with probability theta into R. So the probability that all these cells that are read by a query, if he satisfies this, if he reads that many queries, is this. Okay?
Theta to the power.
Yeah. Okay, from that I want to infer that the probability, I want to show the probability that the number of awesome queries is large. So we can bound this as follows. So let me write this. So we have an expectation of some random variable, and this so the maximum possible value of a number of awesome queries is p. So if in this case, when the number of awesome queries is at least n, you can bound this by p. In the other case, you can bound this by n. And from that, you can deduce a lower bound on this probability. But that's not all. Because remember that we took R at random, independently. But it can be that R is large. And we should upper bound the probability that R is too large. Okay?
Yeah, it should be also easy because
we can use Chernoff inequality.
So every point gets enough this probability theta, which is 1 over log n, right?
Yeah.
So
and we have CI cells,
which is beta to the I times. What is CI? The size of CI?
The size of CI, you can assume that this is at most b to the I t update, but you can assume that this is at least here also by adding dummy cells.
Yes.
Okay? So, and expected size of R is what? Is theta by CI. Okay, so this is theta b to the I t update. Yeah? And we need that the size of R should be this. And the difference between this and this is some polylog. Okay? So you can take theta in such a way that this is smaller than this. And then use Chernoff inequality. This will be small. And this probability should be bigger. Why it will be the case? Because, okay, let's forget n. This will be small compared to this. Because we have something logarithmic raised to the power log smaller than log, just a plain log. Log to the power of 0, 95. So this is smaller than n to the epsilon for every epsilon. You see? That is, this probability will be something. I mean, this is larger.
This is, for example, at least the 2 to the log n to the 0.5. Say.
Yeah. So this is large enough. And this will be, actually, this thing will be a lower bound on this. And this, yeah. So it will be larger than the bound you will obtain from Chernow bound, because it's like exponentially the lower bound will be exponential in this Chernow bound. And this is for if E is something larger than some constant, this is some polylog which will be much smaller than, it's the exponent to some polylog which will be much smaller than this. Okay, but
so the rest was not very clear, but we can do the math here.
yeah.
Okay. Thank you. That's it.